It's annoying, no? But the chalk disappears every time. No, but there's.
Yes. Or it's on a daily basis.
If somebody eats this, I don't know, because yesterday there were 2 pieces, and I don't know, you will probably have 1 lecture more, right? No.
Yeah, 1 tutorial.
Ah, okay, so it's Giovanni. So let me remind you, we started to discuss discovery of the third family of quarks, and the origin of this was attempt to explain CPU violation. And the idea is that you need to have some complex parameters in your theory, your Lagrangian, and the important point is that these complex parameters should be physical, in a sense that you cannot remove these parameters by doing rephasing of the fields, for instance. In the case of 2 generations, we have 2 by 2 mixing matrix. It has, from start, 4 complex parameters. 4 elements, 4 complex parameters. But then unitarity removes one of this, because it gives relation between phases of 1, 2, and 2, 1 elements. And then what we have found that 3 phases can be removed by rephasing of the fields. So you can absorb some phases by redefinition of the fields. So this is 2 by 2. And then Kobayashi and Maskawa tried to overcome this by introducing the third generation of the quarks. And as I have discussed already, the number of, for n generations, the number of complex parameters from the beginning increases as n squared of phases. Increases as n squared. Now, unitarity, and you will have the exercise for this. Unitarity removes some of these phases, or give connection between these phases. So you will count how many of these, and then rephasing allows to remove 2n minus 1 phases. As the starting number of phases increases as n squared, and all other things is just like n, then at some point you may not be able to remove all the complex parameters. And what Kobayashi and Maskawa have found, then already for 3 generations of quarks, you cannot remove all the phases. So they propose to introduce the third generation of quarks, which is made out of top and bottom quarks. And so now we have 3 by 3 mixing matrix. And for the current, in this case, we can write UCT transponent gamma alpha 1 minus gamma 5. And here we have D, S, and B. And now we have here 3 by 3 matrix, which is called Ckm Matrix, Kabiba-Kobayashi-Maskawa matrix. So this is 3 by 3 matrix. So from this you cannot remove all the phases, and you will count how many phases are left. And also you will have exercise that if you have, for instance, 4 generations of quarks, how many CP violating phases are still left. So this is 3 by 3 matrix. And remember, we also introduce D prime states, which is, in this case, will be VCKM times D. And D is this D, S, and P. And for 2 generations, D prime is our D theta and S theta. So let me remind you that what mixing is doing, it connects mass states with states which have definite charge current interactions. So they enter with the same current with U, D, U, charm, and top quark.
In that case, you also need a field in the D prime, like B, I don't know, theta or something.
Yeah, so then it will be also combination. But now, when we have 3 quarks, 3 family of the quarks, it should be more mixing angles. So now you will have rotation in 3-dimensional space. Remember, so that actually can be also interpreted as rotation of the basis. So in 2 quark case, you have U charm, and here is DS. And in 3 generation case, you have 3 angles of rotation, right? So you have 3 angles of rotation and 1 phase. So 1 phase cannot be eliminated. So this is what is the Ckm matrix. Now let me discuss discovery of particles which contain big quark. And this has been done quite soon after this introduction. It was 74, and then 77 particles which contain big quarks has been discovered. So the experiment. So big quark. Experiment had been done in Fermi laboratory in 1977, and the spokesmen of the experimental collaborations were Herbst and Ines. They have studied interactions of protons of high energy, again with beryllium target. Remember that resembles the experiment of discovery of J-psi. And then they detected final states with mu plus, mu minus, and the system of hadrons. So those were high energy protons. The energy was like 400 GeVs. What they measured invariant mass of the pair of mu plus and mu minus. So literally what they saw is that you have proton which hits the target, and then in the final state a number of hadrons, pines, K mesons, and 2 muons, so mu plus and mu minus. And again, suspicion is that this mu plus and mu minus come from decay of a single particle. And so what you do, you measure invariant mass of this system, mu plus and mu minus. And the result was the distribution of these events with mu plus and mu minus over the invariant mass. I will not repeat definition, you have already this. And what they saw, of course, background, which is again related to simple electromagnetic interactions when you have photons, virtual photons, which are transformed into mu plus and mu minus. And on the top, they saw the peak at the invariant mass around 10 GeVs. So the interpretation was that you have here production of a new particle which then decay into mu plus, mu minus. So what has been found actually in the first series of the experiment that it was quite wide peak of say 1 GeV width. still interpretation was that you have production of new particle. So let me put the name. So it's epsilon. It's called epsilon, which then decay into mu plus and mu minus. And you have the rest. Now later it was established when the experiment has been repeated with better energy resolution and with higher statistics, that actually here you have not just one peak but 4 peaks, which merge to some extent if you have that energy resolution. So 4 peaks, you have something like that. And then the 4th peak was quite wide. That was 2, 3, and 4. So you have 4 epsilons produced. And the interpretation was that there were states of composite states of new quarks with excitations. So one is epsilon 1s state, I think you know classification in atomic physics, with the mass 9 or 46, and this is in GeV. This is in GeVs, right? And then the widths in KeVs. And in KeVs it was 1.3. So you see, very narrow, because GeV is 6 orders of magnitude bigger, so the peak is really very narrow. Then epsilon prime, which is excited state, which is 2s. And the mass was 10.02, and the width 44. Then epsilon 3s with close mass 36, 10 GeV, and the width 26. And then epsilon 4, so let me put here 2, and here's the 4th epsilon with the mass 1058, and the width was 10,000 keVs. If someone has idea what happens, why these widths are very small, and the width is the same as the rate of decay, they're very small, and suddenly you have, you see, 1,000 times bigger rate and decay rate and the width. Any idea why it happens so? What could be the reason? Well, it is general. What could be the general reason for this? You see, the mass increases, and suddenly the width becomes much bigger. This means that some new channels of the decay appear, which are not possible here because of smallness of the mass, but here you may have some new decay modes. And so that is most probably due to electromagnetic interactions, and this suddenly this big width, which is 10 MeVs, which is typical for strong interactions. So that for this mass, this is 4s state, you have decay mode and into new particles which have strong interactions. This is why it's very intense. So the interpretation, again let me repeat, is that epsilon is the composite state of new quarks, big quarks. composite state. This is similar to J-psi, which was composed of charm anti-charm quark. So a new quantum number has been introduced, B, beauty. And beauty of B quark is -1, and beauty of B bar is +1. Of course, this is a matter of convenience of so one can, of course, redefine this and introduce plus and minus here gains. So, since epsilon has B and B bar, then beauty of epsilon is 0, and so epsilon is the state with hidden beauty. So again, its analogy is J-psi. Now, the mass of B quark is estimated roughly as a half of the mass of epsilon, and it was something like 4.3 GeVs. So this is real mass. And the mass of epsilon is a bit higher because you have also contribution of interactions to the mass of epsilon. So now what happens is with this epsilon 3, epsilon 4s state. Of course, once you introduce new quark, you can compose new mesons and new hadrons, which include new baryons, which include this B quark. And in particular, the simplest, of course, is this is B meson now, which is composed of U quark and B bar, and B bar, which is composed of UB. So these are the lightest among all, and charge here is, so they are composed of light quarks, so that these are the lightest mesons, which have this beauty. Now it's open beauty, right? So this B has beauty 1, and this is -1. And now what happens is that the mass of these B mesons turns out to be smaller than 1/2 of the mass of epsilon, and therefore you have a new decay mode for epsilon 3 bars as decay into B bar. So these are strongly interacting particles. This is strongly interacting particle, so this is due to strong interactions, and this is the reason why you have very big decay rate and width of the resonance. And now you see here that it's interesting that the change of mass is not so big, right? But this guy cannot decay into 2 B's, so that mass of this B meson is bigger than half of the mass of this epsilon 3s. And therefore, these 3 cannot decay, cannot have this mode. Now, properties of epsilon are quite similar to what we have for J-psi. So epsilon has the spin 1. It has parity minus, like pi, so this is pseudo, so this has -1, and C parity is minus. Now let me discuss spectroscopy of hadrons which contain beauty. Oh, maybe you have some questions?
There you mean that mass of B is less than half of the mass of epsilon triple prime, right?
Yeah. And therefore you have kinematically a possibility of this decay, right? So which means that mass of epsilon its mass is, so mass of epsilon is bigger than 2 masses of B, if you want, I would say. So you have kinematically, you can have a conservation of energy. So now let me discuss B spectroscopy. So we have U, D, S, charm quark, and now we have new quark B. And you can create the states, composite states with all these quarks. I have now a big family, and the same is for B bar, but then it should be U, D, S, and C. So now we have 5 quarks, and the symmetry, flavor symmetry, should be extended to SU5. SU5 flavor symmetry. So B mesons, which I have mentioned, have spin 0, and there are analogies of pi 0, K mesons, and D mesons, so they form the same family of mesons with spin 0, pseudoscalar mesons. And so this family now will consist of how many components? Can you say? So we had SU4, flavor symmetry, and we had 15 components. Now with this SU 24, right, so it's a joint representation. So we can compose the composite state of the type B Q bar and B bar Q. So these are mesons. And so examples of B mesons you had already. It's B U bar, and this is B minus, the lightest. So B bar U, this is B plus. Now you have also states B D, which is B 0, and you have states B bar, B D bar, and this is B 0 bar. And so this state, right, and this state, they form isospin doublet, and these two also form isospin doublet. Now the mass of B mesons is 527.9.15 plus minus 0.31 MeVs. So you see it's so 5.3 GeVs. Now they have spin 0 and parity minus. So the same as pi meson, K meson, and D meson. The lifetime of this particle is 1.638 plus minus 0.0. Probably I should not put this error bars, they change because statistics increases. 10 to the minus 12 seconds. And this is typical time for weak interaction decays. So the story is the same as for K mesons. Those are the lightest. So these particles are the lightest particles, mesons which contain a big quark, have a beauty. And therefore they can decay not due to strong and electromagnetic interactions, but only due to weak interactions. Okay, again, the same story as it was also with D quarks, with D mesons, and then with strange K mesons, and now this is the same story with B. So again, saying this, introducing this SU5 flavor symmetry means that you have Lagrangian of strong interactions, which is invariant under SU5 flavor transformations. Of course, this symmetry is strongly broken because masses are quite big. You can compare with mass of, say, pi which is 0.1 GeV, and here we have 5 GeVs. So masses within these 24 plate strongly different, right? So which means that you have strong violation of the symmetry by mass terms. So the interactions, and we will see interactions with gluons, which are the strong interactions, they are invariant under SU5. However, mass terms are not invariant under SU5. And of course, you have strong manifestations of this violation in processes. Now let us study the case of B mesons. So lifetime is weak interaction lifetime. And this is important for our mixing, what we started with. B plus have mode of the decay into D0, L plus, and nu L. So we have leptonic pair, and L can be electron, muon, and also tau, because B has a big mass. No, probably tau not for this, but certainly you will have this. I think you have also decay. You can check what is the big mass, the kinematics is okay or not. So what is the diagram for such a decay? We have B plus, which is composed of U quark and B antiquark. U is spectator quark, and then B is transformed to charm with emission of leptonic pair. Okay.
Anti-charm.
Anti-charm, right. And so this is D, 0 bar. So which means, so observation of this decay means that we have transitions of B quark to charm quark, or B antiquark to charm antiquark. Right? So I will describe this transition that it is proportional to element of mixing matrix VCB. Now, what has been observed also decay of B mesons onto usual quark. Not strange, not charm. B plus has also mode of decay D0 bar. Decay mode into pi 0, and then L plus and nu L. And for this, we have the diagram. U, here is B bar. And B should be transformed into U bar to have pi 0. So this is pi 0 with emission of the pair. So which means that we have also transition of B quark to U quark. Right? And this, what we describe by B U B element of mixing matrix. I will come to this. So observations of these decays are extremely important for CP violation. So remember we introduced 3x3 mixing matrix. But to have CP violation, you need to have all elements of this matrix, or well, you need to have non-zero elements. Practically all these elements should be non-zero. So if you would have something like this Ckm of the form, when you mix only two and the third is not mixed, then you would not have a CP violation. So you need also mixing of all the quarks. So now with this B, we have we have doublets which form the current of the following form. You have U, and U contains, now it contains a component of down quarks, which is mixture of all three. So it contains D, S, and this is VUD plus VUS, and plus VUP element times P. So remember, in the case of two generations, we had U quark staying in the same doublet with just D and S. And remember, that was cosine Cabibbo angle, this was sine Cabibbo angle. Now we generalize this picture, and the observations of this type decays, which imply transition of B to U, means that you also need to put in the same doublet also B quark with some mixing parameter V, which then is appearing in this decay. Now for charm, now we have three doublets. We have U, C, D, D, plus V, C, S, S, plus V, C, B, and here is B. So also in the second doublet with charm,
That is small b.
we have yes, yeah, small. What do you mean small? Here, BCB. So we have also a component of B quark, and therefore we have current which transforms charm to B or B to charm. So discovery of these decays proved non-zero values of this. And then for top, of course, you have orthogonal combination, which is VTD D plus VTSS plus VTP and P. Okay. So now we have mixing matrix composed out of these mixing parameters, and they form 3x3 mixing matrix.
The top part was discovered until later, right?
What? Top was discovered in '95. So that's discovered later because the mass of top is much heavier. So it's more complicated stuff. I don't know if I have time to discuss top discovery, top quark. That probably will go to the standard model part, because top quark is very important for Higgs sector and gives important corrections to the mass of the Higgs boson. So this type of things will be discussed in particular in the standard model course. Questions?
You can't have a B decay into a K, right?
B decay into, yeah, I will discuss this. Yes, you can have also decay, but this is important for testing the presence of these parameters.
So you had a mixture between bottom and strange?
This is flavor changing neutral current, right? Because B has the spin. I will discuss this type of the modes. So there is no direct transition of B to S. It appears, as we discussed also, transition, remember, K, so strange quark to usual D quark, but it goes through the loop. It's not the lowest order effect. But this is the level that appears in the currents. Probably I will add some more about the mixing, because eventually CP violation effects are, of course, due to this complexity of these mixing parameters. And numerically, this effect also proportional to certain combination of this of the moduli of these particles. So now we have Ckm matrix, which is in the first approximation is just one. So the biggest elements are diagonal elements. The biggest non-diagonal element is VUS, which is approximately VCD. Maybe I should write it. I don't know if I have too lazy to write it. So let me just write some proper elements. You have this V, but those are written here. So let me do the following. I'll do the following trick. Okay. So I have this, I believe. So now mixing matrix is made out of these parameters. And you can write, so we have this matrix, which is VCKM. I believe this is VCS. Okay, so this is 3 by 3 matrix. And remember what it is doing. So this VCKM connects D prime, VCKM. This is D. This is DSB. And so these are mixings of these which enter with U charm and top. So this is the matrix, if you want, which connects mass states of down quarks and upper quarks in doublets in charge currents. Okay? So now, these elements are close to 1. The biggest off-diagonal elements are those. And in the first approximation, so that is Kappa angle. Right, so it's approximately sine theta Kappa, which is 0.22. And sometimes people are introducing this as a lambda notation for this sine theta. Now, VCB is this element. So next in the size, and this is of the order of 0.04115 plus minus. Let me this is central value, and this is of the order of lambda squared. So it's square of Kappa angle. And what you can measure the ratio of V. I will write here. So you can measure the ratio of VUB over VCB. And you can extract this from the rates of two processes I have already shown. So this can be extracted from the ratio of gamma, and B go to pi 0 L nu over B go to D0 L nu. So remember, these are the processes which I have written before. And this one is proportional to VUB square, this one to VCB square. And therefore, measuring this ratio, you can extract this one. And it turns out that this is approximately 0.08. And now knowing this VCB, you can find what is VUB. VUB is 0.0036, and this is approximately a lambda cube. So what we can conclude that there is a hierarchy of elements of mixing matrix. The biggest one is this one, off diagonal. Then These go, and this is the most remote from this unit matrix. This is the smallest one, and also this one is the smallest one. As I told you, we still don't know what is the theory behind this mixing parameters. We'll introduce some family symmetry, some kind of Progat-Nielsen idea that there's U1 symmetry behind this hierarchy. So this is open question. This is what we still need to explain. So that's key point. Now Wolfenstein proposed parameterization of this mixing matrix using these lambda parameters. And there are complex parameters in various places, but in particular here and there. So that's what leads to 2CP violation. Any idea how to explain this hierarchy of mixing?
Looks like coupling strength, like 3 levels. To go from one mixing to the other, you have to go to 3 steps.
Yeah,
Coupling parameter.
well, that's obvious. But so which kind of the couplings? Because we have to deal here with this mixing matrix, right? So these parameters enter different charge currents. Okay. So the overall coupling is known as G Fermi, and but then there are kind of mixtures. Of course, you can observe immediately that light quarks have a dominant connection to the light quark. So U mostly couples with the lightest D quark, less strong with the heavier strange quark, and even less with B quark. So for the second line, see you have this type of the hierarchy that charm quark mostly couples with strange quark, which is closer to mass. So this kind of connection to the mass. Yeah.
So do you think like charm?
So beauty likes top. So the biggest coupling is with top quark.
I see.
That's his partner, but then he has still some touch to other. So for B, see, the biggest one is this one, close to 1. So this is lambda square, and this is lambda cube. Okay, so now you see actually here this VUS and VCD are not just this Habiba angle. If you do now parametrization in terms of triangles of rotation, then what is staying here is, say, sine theta 1, 2, which would be kind of analogy of sine theta Habiba multiplied by cosine theta 1, 3. Which is of this order, so this is very close to 1, so that's why this parameter is essentially this sine theta Habiba, and the same is here. Now let me say a few more words about the phenomenology of B, or beauty particles. It's very rich, actually, much richer than, for some reason, than for chat. Sorry?
What is the main decay channel of the B mesons?
Well, it depends which one you mean. You need to tell me what is, and you will have exercise, by the way. I don't know how far I can go. But these are weak interaction decays. Well, again, which meson? You have to tell me.
B meson.
The lightest one.
Ah, okay. There too. Doesn't matter why.
Many. So what you have B plus, B minus,
Okay,
B0, B0 bar. These are composed of B and the lightest quark. But then you have BS, which is composed of B quark and strange quark. You
Okay.
have
This is
BC, right? So many.
The latest one?
So let me.
Okay.
These are weak interaction decays. Yeah, you need to count it. Now neutral mesons. And there are two, B0, which is composed of B bar and D, and B0 bar, which is composed of B and D bar. What is interesting that these methods have no definite mass, but they are mixed. So there is a B0 bar mixing. There's also this K0 bar mixing, which we will discuss in details later. So which means that B0 and B0 bar have no definite masses. So they are composed of some combinations of this B0 and of states which have definite masses. And so you expect phenomenon of B0 bar oscillations. So that leads to oscillations. Again, speaking about mixing, we deal with two sets of the states. These are the states which have definite beauty, right? So you have B0 bar, and the states with definite beauty. But they are mixtures of states with definite masses, say B01 and B02. So these two guys have definite masses. And this is because you actually have interactions which transform B0 to B0 bar. That appears in high, so in the loop, at the loop level. So there are interactions which actually transform B0 to B0 bar, and this is the origin of mixing. And this is the origin of the fact that some other combinations of these two have definite masses. These have definite beauty. So these are kind of interaction states, have definite interactions, strong interactions. Those are mass states, and they do not coincide. So you have cosine, sine, minus sine, cosine, which is close to 45 degrees. Now the difference of masses of B1 and B2, and that what determines the oscillation time, is 3 × 10⁻⁴ electron volts. Very small in comparison with the mass. So they have masses around, for this B is 5 GeVs, 5 or 3 GeVs, an extremely small mass split. And this is because of weak interactions. Actually, weak interactions can transform this to that one. Because here you have violation. To have transformation of this B0 to B0 bar, you need to break beauty, right? And therefore, that can be due to weak interactions. And therefore, that produces very small mass split. That has been measured because the observed effect of oscillation, so to say, transition of B0 to B0 bar, and so periodic transformations of this type. B0's decay, and in fact, delta M over gamma, and this is decay rate, it's not far from a unit, 0.723. This means that the process of oscillation, the time of oscillation, is comparable with the time of the decay, and you need to consider these two simultaneously. So you have in contrast, for instance, with neutrino oscillations, when you have oscillations, the decay is negligible. Here you have both processes simultaneously, decay and oscillations. So another point, interesting, is flavor changing neutral currents with B. The process of the decay of B0S, which contains strange quark, to mu plus, mu minus has been observed. But it's very strongly suppressed, as we had also in the case of strange K0 mesons, right? So this particle is composed of B bar and S. And such a decay implies transition of B to S, which is flavor changing neutral current. So B and S, of course, have the same charge, minus 1/3. And such a transition implies transition of B quark to S. This happens again at loop level, quite similar to what we have for K0 decay into mu plus and mu minus. Branching ratio for this decay is 3.2 plus. It's bigger, but probably now the errors haven't checked this year, minus 1, 2, 10 to the minus 9. Which is comparable smallness to what we had in the case of K0 to mu plus, mu minus. And this is again due to diagram with loop, the same as we had in the case of K0 decay. Okay. One more comment, people have studied CP violation in the decays of B mesons. And one of the important channels, and I think you have an exercise to draw the diagram for this process, is decay of B0 onto J psi. So there's an interesting and important mode when we have B0 decay into J psi plus K0S. And you compare this decay with decay of B0 bar. So CP manifests itself when you change particle to antiparticle and then compare modes of the decay. So this is important for CP violation. I'm telling this just to illustrate that the physics is very rich and there are many different phenomena in just B. So this is not accidental that we are talking about B physics. So it's B physics because there are many, we are not actually talking about, say, charm physics. Well, we were saying something, but it's not as rich as we have here. Now let me discuss or give you some idea about so-called B factories. So not only we have this large number of different channels of the decay. So one actually feature is that B is quite heavy particle. And therefore, as we will learn later, you can account strong interactions because strong interactions become weak when you go to high energies or big masses of particles. And so you can, to some extent, have a good description of different processes with B mesons. So that's also helpful. Now, to study properties with beauty particles, people created so-called B factories. So usually we refer to factories as to machines which produce huge number of B particles. The idea is the following. You accelerate electrons and positrons, and you have collision of electrons and positrons. You adjust the energies of this electron and positron in such a way that you are sitting in the resonance of Epsilon prime, prime, prime. So first of all, it's resonance, and therefore the number of events increases. And you produce this epsilon prime, 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 because it has dominant decay mode into B and P bar, as we discussed. So this is basic idea of this B factors. You have a plus and minus at certain energy, and this epsilon primes quickly decay into BP bar. And actually a number of detected BP bars are billions, several billions of BP bars were produced at these B factories. So there are two B factories. One is bar, and that was at SLAC. And at SLAC there was this E plus E minus collider, right? So they use this now to produce these B mesons. And another one is Belle in Japan at Keck laboratory. Again, using E plus and minus collisions and accelerators with E plus and E minus. Important feature of this B factor is that they are asymmetric. You have asymmetric collisions. Which means that the energies of electron and positron are different. In this case, your epsilon is produced not at rest, but it's moving. So you boost, in this case, what we have. So boosted epsilon. And this is useful because this epsilon is moving from the collision points, and then it's better to then explore the interactions of epsilon, decay of epsilon. Because in the collision points, everything is messy. You can have many things produced in these collision points. But if your epsilon is moving out of this central point, and then you can better explore its decay modes. Just to give you an example, I think one of the exercises is very so it's E minus N plus collision. And at bar, you have 9 GeVs for electron and 3.1 for positron, GeVs, and 8 in Belle, 8 GeVs for electrons and 3.5 GeVs for positrons. The luminosities are huge, so luminosities at these factories are something like 7 10 to the 33 centimeters minus 2 second minus 1, and as I said already, a few billions of B mesons have been produced. There's another machine which actually studies properties of B mesons, is LHCb. So at LHC there's also a detector devoted particularly to study properties of these B mesons. I have written asymmetric, right? So with 2s, asymmetric, right? Asymmetric collisions. Now LHCb works not like a collider, but as a fixed target experiment. So the target is at rest, and then protons hit the target. And this is again multi-detector instrument here. There's different detectors, and so here Bs are produced, and eventually identified and their properties have been studied in these detectors. I think there are more. And what are the goals of this B factories? Is to do spectroscopy, to study CP violation effects. And the idea is the following. So CP has been discovered in K meson system, as we will discuss later. And the idea is that maybe in some other decays, in some other processes, CP violation will be not dependent on what you had already in K0, K0 bar. So the idea is to search for or test this Kobayashi-Maskawa idea. And maybe in different processes you will observe different effects of CP violation, which would require some more phases or some other sources of CP violation. So again, I said that you may have some other complex parameters in your theory which produce CP violation, for instance, vacuum expectation values of the fields. Or if you introduce some new physics like supersymmetry, so usually you have some other sources of CP violation because you introduce more couplings. And in general, you will have some other complex parameters which give contribution to CP violation effect. And so the idea is to study as much as possible different processes when you can have CP violation manifestations and to see if they match each other. But for time being, the conclusion that everything can be just described by the simplest Kobayashi-Maskawa scheme. So everything can be described by just a single phase, which appears in this Ckm matrix. Then, as I said, people are discussing oscillations of K mesons, measures the mass split, and again, the goal is to search for some new physics. Nowadays, the main objective is to find something beyond the standard models. Fortunately, everything practically well described in the standard model. When you go to B, to heavier particles, right, then you may have more hope to observe some new physics if it is at high scales, right? So you can imagine that there is some new physics, some new particles with masses, say, above electroweak scale, which is something like 100, 300 GeVs. And then you may expect that in the first place they will manifest themselves in decays, for instance, heavy particles like B mesons. Now, and as usual, maybe B decays indeed is the first manifestation of something beyond the standard model. This kind of usual situation that there are some anomalies. We are saying still some anomalies exist. Still some processes, some probabilities not quite well described by the standard model. So to say, there are some deviations. That can be just statistical deviation. It can be some systematic, just experimental fact. So it's interesting that, yes, nowadays the only anomalies which we observe in high energy physics are some anomalies related to B decays. And so what we call now B anomalies. So one of the recent papers was just on November 15. That was review. Maybe some of you will work on these anomalies, if they will survive. So let me just briefly, but I don't want to confuse you because this is something which is beyond the standard model. So maybe next year these anomalies will disappear. And we had in history a lot of this type of things. So first some deviations are observed, but then statistics increases and so they disappear, or experimentalists find some systematic errors which were not taken into account. So there are two anomalies in B physics. And one is related to so-called excess of events of the type B, decays and D star. This is charm particle with spin 1 in contrast to usual D. And then tau, and then nu tau. So it turns out that there's excess of events, more than is expected. And the best way is to compare with some other decays of this type. And what has been compared with decay of, again, to D star, and usual L and nu. Say this is L is mu and collector. So we have kind of violation of say universality for charged leptons in this case. So it seems that the mode with tau lepton and tau neutrino has a bigger rate than with muon and muon neutrino. Of course, there is some, you need to take into account also the difference of masses. But nevertheless, so this is what we call branching ratio R D star. It's something like 3.8 sigma above expectation. So this is branching ratio. So I need to rate, if you want, I can write it. So branching ratio more precisely for this mode and branching ratio for that mode. So another anomaly is related to another ratio. Actually, let me probably say that this implies transition of B to charm and L and nu. So this is related to charged current. So another anomaly is related to neutral currents. So what has been measured, again, the ratio of K star, which R K star, which is branching ratio of decay B to K star, mu plus, mu minus, over the same for E plus, E minus. So in this case, one observed deficit. So that's smaller than was expected by something like 2.5 sigma. So my opinion that this is something which we just don't understand, maybe the strong interactions quite well taken into account. But anyway, so this is flavor changing process, and what is behind this transition of B go to S and then leptonic pair L plus, L minus. So this is at loop level when B go to S. This is at 3 level, it exists already. So you are listening and forget about this. Let's see what will happen. I'm just giving you an idea that what I'm discussing is not like physics which is say 20 years or 30 years old. So people continue intensively studies of the things. B factor is, Bell is working, LHCb is working, producing results. And so this what actually triggers many papers written. So nowadays people are writing papers to explain these anomalies. Questions?
How significant is that 2.5 sigma?
Yeah, it can be statistical fluctuation. We have examples, of course, when we have even 4 sigma, which is then disappears.
Can you say this? How many sigmas above does something have to be like?
Yeah, it's 5 sigma. So people are saying that if you have 5 sigma, then that is the discovery. If you see some observations which say 5 sigma deviate from expectation. I see.
3 sigma is 95% of certainty of.
Oh, 95. So look, okay. So 95 is just 2 sigma.
Oh, 95.
Now 3 sigma is 99.7. So which means you have 0.03% probability, and 5, I don't remember already by heart, it's 10 to the minus 5, 10 to the minus 6 probability that it's accidental. So, well, Higgs discovery was announced when the sigma was more than 5 sigma. People waited. That's 5 sigma. Oh, but that depends on personalities. Nowadays, theoreticians start to work on some 2 sigma deviations, because they're eager, to do something. There's no deviations, and even 2 sigma, they jump and start to write papers. 2 sigma.
Does it happen that some process have been detected with 5 sigma and then it was an accident?
I hadn't heard about this. Oh, yeah, sorry. But it's like, superluminal neutrino, for instance. Some years ago, that was an announcement by Opera experiment, actually here in Italy, that they see effect of superluminal motion of neutrinos, and then it was just bad electric connection behind this discovery. But, But of course, you need to have 5 sigma and better have 2 experiments, like it was in the case of Higgs discovery. Then you are sure. So there were, of course, some observations, some deviation more than 5 sigma.
Because, for example, Dama Libra has like 10
Yeah. It's or this now mini boon at LSND. At LSND, they have more than, I think, 6 sigma if you combine access. But if the experimentalists are not cheating, this means that they see some effect. A different thing is what is interpretation. So Dama Libra sees some variations, annual variations of the signal in this detector, and so the interpretation that they see dark matter effects. Perfectly, but then there were some statements that maybe just because of change of humidity or background, muon background. So probably if they are not cheating, there is something behind. But most probably it's not dark matter. Actually, in Korea they have experiments similar to that. Let's see what they will find. Okay? Now, in the end of this lecture, I will start to discuss how we sure that quarks are really objects inside the hadrons, inside the nucleons and mesons. You see, I started my studies in 70s, and at that time people still doubted these partons are really quarks. But quarks is something which gives you classification. Good. But these are not real objects. That's what it was a dominant idea, that this is something which is useful, but it's not like something which is sitting in the proton or neutron. Now, how do we know really, how we convince ourselves that quarks are really objects inside the nucleons, and mesons, hadrons? So I want to study structure of hadrons. So we need what? We need to take microscope and to see if our proton and neutron consist of something, right? Like in Rutherford experiments, again the repetition of the same story. Let me make one comment. So I understand that my course is difficult in the following sense. It's a lot of information. It's not like, like in some other courses like group theory, when we have logic line, it's a new development. A came from B, B came from C, C. Right? So many things, and this is how actually science developed. But at the same time, there are many repetitions in nature of the same things. So if you find a way to remember this, then it will be easier to have this, to understand connections. On the basics level, there were not too many actually things in terms of principles and concepts. Not many. It's just different manifestation and repetitions. And discovery of the structure of hadrons is also repetition, right, of what we already learned before. And this is the first step to understanding that quarks are real objects, which are sitting inside the proton, neutron, and other mesons. So we know that the size of hadron, the size of the proton, like the simplest nuclei, is something like 10 to the minus 13 centimeters. Right? That corresponds to momentum, which is 1 over h 0.1 GeV. And this is roughly the mass of pi, which is not accidental, right? So this, the simplest theory of strong interactions is based, as you cover, right? And strong interactions are due to exchange of pi. And the radius of these interactions is inverse of mass of the pi. To probe structures which are smaller than this, we need to have microscope with wavelengths which is smaller than this. So naturally, right, it's clear. So we need to have microscope with wavelengths which is much smaller than h. Or we need to organize scattering with effective momenta which is much bigger than 0.1 GeV. So we need to consider scattering with momentum transfer much bigger than 0.1 GeV. Then you probe structures which are much smaller than 10 to the minus 13 centimeters. So that's momentum transfers even more kind of correct characteristics. So you need to transfer momentum to your system and then to see what is the reaction of your system onto this transfer of the momentum. And this way you are probing the size of the system. So what you need to observe to have big Q transfer momentum, scattering on large angles. Because transfer momentum is given by momentum multiplied by mixing angle, okay, sine theta scattering. So it's not just enough to have your particle which has big energy or big momentum. You need to transfer this, and you need to have Q, which is given by this P sine theta, and therefore you need to consider scattering on big angles. That was actually in a Rutherford experiment when I observed scattering of alpha particles on the big angles. So what you need to consider the processes with transfer momentum, which is comparable with momentum, which is comparable with energy. You have relativistic particles. So we introduce Q square, which is minus Q square, positive characteristic, because if you have scattering in T channel, the Q square transfer momentum is negative. So let me put it this way. And that should be bigger than 1 GeV squared to quantify, so that Q itself is bigger than 1 GeV. Then in this case you are probing the structures which is at least 10 times smaller than the size of the nucleon. And of course then you need to have energies of your particles at least, so 1 GeV or bigger. Conclusion that to probe inner structures of nucleons, you need to have collisions with energies bigger than 1 GeV and consider scattering on big angles. So that type of the scattering will probe the structures within the nucleon. That was what has been done in so-called deep inelastic scattering. And now let me discuss deep inelastic scattering. Well, elastic scattering, when you scatter, for instance, two particles, and then in final state you have the same two particles. You do not produce some other things. So this is elastic scattering. So when you have some more particles in final state, this means you produce new particles, which means that you have big transfer of energy, momentum, right? So which means that if you want to have this type of the measurements, you need to study deep inelastic scattering. And what has been studied extensively is the scattering of electrons on protons. And in final state you have again electron and then the system of hadrons. Or you can draw this as you have electron, which scatters due to electromagnetic interactions. You have proton in initial state, and then you transfer big momentum in this way to proton, and you observe some secondary particles. You have deep inelastic scattering. And this is the process which you need to study to probe the structure of the proton. So studies of this type of the processes, deep inelastic processes, led to very interesting result. So the result is, and you probe here electric charge distribution in proton, so to say. Remember, in reservoir scattering, what was probed is the distribution of positive electric charge inside the nuclei. And the issue was if this electric positive charge is distributed, say, uniformly within the atom, or it is focused on, concentrated in some small regions of parameter space. The story repeated here completely. We know that proton is charged, and what happened is that the scattering looks like this electric charge of proton is not uniformly distributed inside the proton, but again it is concentrated on some much smaller size objects within the proton. So important conclusions about the result of this scattering, and I will then explain, draw some theory, is that electric charge, and by doing this electromagnetic scattering we are probing electric charge distribution, right? So for instance we will discuss that also proton contains gluons, but they are neutral, and we are not probing gluons in this way or some other neutral stuff. So we are probing how the charges are distributed. So electric charge of proton is not distributed uniformly, but it is concentrated in small size objects. Much smaller than the size of the nucleon. So these objects looks like point-like, but at least you can say immediately that the size of these objects are much smaller than 10 to the minus certain centimeters. So, which means that nucleons, proton, neutron, are composite states of point-like objects, and the scattering results indeed correspond to, and I will discuss this, that scattering proceed on the point-like objects. So structure of these objects doesn't show up. And these point-like objects carry electric charge. And these objects were called partons. And immediately the question was, are partons quarks or not?
Could we also tell in these experiments that, well, two of these regions are positively charged and one is negatively charged, corresponding to two of quarks and one down quark?
Yeah, purely we don't know. So, and we see, yes, in fact, there are positive and negative charges.
So could we tell that from this experiment that two of them are positively charged and one of them is negatively charged?
Yes. So eventually, detailed study actually showed this. So it looks like nucleons have the following structures that are point-like objects inside, charged, and they produce the scattering result. So what is the confirmation of this picture is Bjorken's scaling in the first place, and that I will discuss on Friday, friends. It's what actually leads us to this picture is Bjorken's scaling. So results of the experiments and their interpretation using Bjorken scaling leads us to this picture. Questions?
Have we ever tried to do it with electrons to see if they're composite states?
Sorry?
To see if electrons are composite states, have we tried to do a similar experiment?
Yeah, so what we can do, we can scatter electrons on electrons and to see if this produces some deviation from point-like structure. For the time being, we haven't found anything. So remember, I discussed in the first lecture compositeness of quarks. Since we have quark-lepton analogy, most probably the structure of quarks and structure of electra, so if it exists, right, is quite similar. And so we check this up to 10 to the minus 18 centimeters that quarks are point-like. For electrons, we have no such high energy collisions. And as Peskin explained us, right, because of synchrotron radiation, unfortunately, we are still dreaming to have this 500 GeV electron collider. So with this, we are not checking, so at least we can check by this, say, one order of magnitude bigger sizes. I think you can put the bound something like 10 to the minus 17 from the scattering. Well, now it's even less because the highest energies were at LHC, which is 100 GeV times 100 plus 100 GeVs. You have 100 GeVs plus or minus collision. And the result of scattering has no deviation from point-like structure of electrons. So, which means that we are probing something like inverse of 100 GeVs by this, which is a few 10 to the minus 17 centimeters.
This conclusion sounds very similar to the discovery of the nucleus.
Yeah, so, yeah, sure.
They also thought that it was point-like.
Well, nuclei, right? So the nuclei has the size much smaller than the size of atom. Because nucleons inside the nuclei they are quite packed, so it's not like they are point like inside the nuclei. Okay? Okay, so then see you after tomorrow, right? So you will continue with Bjork and Skellen. Recording.